Hello and welcome to another WJEC A level physics question. This is question 2 from June 2013's Unit 4 paper, and it's about specific heat capacity, which nowadays is found in Unit 3. So what we've got here is a container made of an insulating material, contains 1.7 times 10 to the minus 3 meters cubed of water. And the water is heated by a 3 kilowatt electric immersion heater, and the student records the water temperature every 0.5 minutes. Given that the density of water is 1 times 10 to the 3 kilograms per meter cubed, we've got to calculate the mass of the water. Well, mass is density times volume, so 1 times 10 to the 3 times 1.7 times 10 to the minus 3. Well, these two power bits cancel, so we end up with a mass of 1.7 kilograms. Next, we have to plot a graph of the water temperature against time in minutes, so I've pre-drawn this. Just got to be careful that we plot points to within the nearest half of a small square to get the full marks for the line. You can see it's a pretty good straight line. I've extrapolated it backwards and I've also extrapolated it forwards for the rest of the paper. So estimate the original temperature of the water. Well, looking at this graph, it seems to be about 20 degrees Celsius, which would seem reasonable. That's a sort of typical value for room temperature. And if the heating continues, how long after the start of heating will the water boil? Well, again, I've boiled it at 100 degrees, dropped the line down, and we seem to be at about 3.2 minutes. I've seen lots of people misread this scale. Every 2 little squares is worth a 0.1 of a minute, so 3.2 minutes here. You can give the answer in seconds if you want, but as long as we've got a unit, 3.2 minutes is fine. The power of the heater is 3 kilowatts. Determine a value for the specific heat capacity of water in the insulating container. Well, specific heat capacity is the energy supplied over m delta theta. And if we put in some values, well, the total amount of heat supplied depends on how long the heater is running for. So let's allow it to run for 3.2 minutes. So Q is going to be 3.2 minutes turned into seconds and multiplied by the 3 kilowatts for the power. The mass we've already seen is 1.7 kilograms. Now in the full 3.2 minutes, the water temperature has risen from 20 to 100 Celsius, so delta theta is going to be 80. So we can plug some values there into the calculator, and hopefully a little bit of general knowledge will tell us the answer should be somewhere around 4,200. But with experimental results we never get things exactly as we expect. So here we end up with 4,235. And unit either joules per kilogram per degree Celsius or joules per kilogram per Kelvin. I wouldn't probably, as a final answer, leave 4 significant figures, so I would probably round that and call it approximately 4,200 joules per kilogram per degree Celsius. And that's a good answer because that's what we're sort of expecting. So the key here is to match the time, 3.2 minutes, to the temperature rise. You can choose any time as long as you've got the corresponding temperature rise. For part F of the question, the student repeats the experiment but uses a container that's not such a good insulator. Readings are obtained at the same time intervals as before. State what happens to the values of the temperature and so on. Now, because it says state, there's no need for an explanation. So number 1, the values of the temperature, they're simply going to be lower. If we're asked for an explanation, we would say because some of the heat energy has been lost to the surroundings, obviously the water is not going to heat up so quickly. For part 2, that means that the gradient of the graph is going to be lower as well, because again, for each sort of time interval, the temperature gain will be less than it would have been with the better insulator. And for part 3, we've got to work out what happens to the value for the specific heat capacity here. So if we look at this equation that we've used on part E, C and delta theta are inversely proportional, provided the same amount of heat and mass have been provided here. So if we've got smaller temperature change, we're going to get a higher value for the specific heat capacity. So thank you very much for listening. Please remember to like and subscribe and add any questions to the comments below the video. Goodbye.